Hey friends, remember that in dark times Christians have more influence than ever. When people are in darkness, they look for light, they look for answers, they look for hope, they look for love. So 2 Corinthians 4 verses 5 and 6 say, "It is not ourselves that we proclaim Christ Jesus as Lord and ourselves as your servants for Jesus' sake. For the same God who said, 'Out of darkness let light shine,' has caused his light to shine within us, to give the light of revelation, the revelation of the glory of God in the face of Jesus Christ." I just heard about a priest in Italy with the virus who gave up his respirator to someone else. The other person is living and the priest died. That is shedding light. Hopefully, when people look at us, they will see the face of Christ. This is the only topic that is not covered in the textbook. It's going to be related to something from section 6.5. And so on Brightspace in the example spreadsheet notes folder, there is a note packet, section 6.5 extra reading, and then 2 Excel files, tablet and reading, that I'll be using. The note packet looks like this. So why are we covering this if it's not in the textbook? The reason is that this type of hypothesis test is probably the most useful of all. And on your projects, you may well have reason to want to do this. And since it's very much related to section 6.5, just pushing it a little farther, I think we can push through this. So the situation now is that we have two different populations, and they would each have their own population mean, and we're trying to check whether those two population means are different or whether one would be larger than the other. Let's just jump into several examples here. First one, the statistics department wants to evaluate the effectiveness of two teaching methods. So they divide the students into two groups. Group 1 is taught by lecture, and Group 2 is taught by having the students do worksheets. Then they take a sample of 20 students from each group and have those students take the same test. The mean scores of the 20 students taught by lecture and the 20 students taught by group work or worksheets are computed. We could compare those two numbers, but the real interest is whether the population means would be different. In other words, of all students who would ever be taught by lecture, that mean would be mu sub 1, we'll call it. And of all students who could or would ever be taught by worksheets, group 2, their mean would be mu sub 2. X1 bar and X2 bar are our means in the sample, but we're really interested in knowing something about the means in the population. So in particular, the department wants to know if there's a significant difference in the effectiveness of the two methods, which we could restate: is there a significant difference in the mean test scores of the two groups? And so I'll go to the alternate hypothesis and say what we're trying to decide is mu1 not equal to mu2? The null hypothesis, the status quo, would be that mu1 is equal to mu2. So the null hypothesis says, nope, no difference in the two methods. Alternate hypothesis says, yeah, there is a difference in the test scores between students who are taught by the different methods. Or how about this? There's a shoe manufacturer that keeps hearing rumors that among US adults, the average length of the left foot is greater than the average length of a person's right foot. So this manufacturer gets 60 adults as a sample and measures both feet of each of the people. They compute their sample means for the left feet and the right feet, call those X1 bar and X2 bar for the left foot and the right foot. And then we're interested in knowing, well, what about the mean foot length of all US adults? Mu1, mean foot length of the left foot of all adults, mu2, mean foot length of the right foot of all adults. Are those two different somehow or not? And in this case, the rumor is that the left foot is greater than the right foot. So the left foot is mu1, and so we're trying to check if mu1 is greater than mu2. That's the alternate hypothesis. So the null hypothesis would be mu1 less than or equal to mu2. And third example, trying to decide whether advertising is effective, whether it's persuasive at changing people's opinions about the product that is being advertised. So 20 people participate in a psychology experiment. First, they answer a questionnaire and they rate Coke products on a number of factors, taste and value and so on and so forth. Then they each watch a 45-minute video of rich, famous, good-looking people attributing their success in life to drinking Coke. Sounds like standard TV advertising, right? Everybody in a TV ad is rich, famous, good-looking, and can't live without the product they're selling. Then the next day, the participants go back and answer almost the same questionnaire. And the question is, will people's impressions of Coke change? More specifically, will they improve after they have watched the video? So let's let mu1 be the ratings given to by all Americans who have not seen the video, and mu2 the mean rating given by Americans who have after they've watched the video. We know what happens with the sample means. We're interested in saying what happens with the population means. And specifically for the alternate hypothesis, we're checking whether the mean of all people after watching the video, the mean rating for Coke is greater than it was before the people have watched the video. And so the null hypothesis is mu1 greater than or equal to mu2. Okay, so that's a bit about how you set up hypotheses when there are two populations and why you would want to do so. Then, if you're getting ready to do a hypothesis test, you have to decide whether the samples are independent or dependent. So we'll say that two samples are dependent if there's a natural way to pair members in one sample with those in the other. And if you can't think of a way, or there doesn't seem to be such a pairing, then the samples will be considered independent by default. Let's go back and look at these examples. So here we had 20 students in one group who had been taught by lectures, 20 students who had been taught by group work. There doesn't seem to be any connection between those two groups of 20. And so the default is that these two samples would be independent. In group 2, or case 2, I should say. So now we have the mean length of the left foot of 60 adults sampled, the mean length of the right foot of 60 adults sampled. Is there any connection between the left foot measurements and the right foot measurements? Well, sure. The same adults had their left feet and their right feet measured. So the connection is actually literally the person's body. I should keep the left foot from one person paired with the right foot from the same person. And so these are dependent. And pair left and right foot of same person. In the third case, there are 20 people before they see the video, 20 people after they see the video, and it's the same 20 people. So now I definitely want to pair again. In this case, I pair a person with themselves. More specifically, I pair their opinion before they see the video with their opinion after they see the video. Why do I want to do that? Well, I'm not really so interested in what people think about Coke. There's a lot of variation among people. What I'm interested in is whether the video changes a person's opinion about Coke. So I want to compare before and after among the same people. This is another case for using dependent samples, and pair each person with themselves before and after. This is a very, very common way that hypothesis testing would be done involving dependent samples, because we often have a before and after situation. Okay, let's do a couple of examples. In the first one, a manufacturer of a medication is developing a new type of tablet. So the idea is when a person takes a tablet orally, the tablet goes into their digestive system and it's to be absorbed, preferably quickly. And the type of tablet, the material of the tablet may have some influence on how much of the medication is actually able to be absorbed. And so the manufacturer gets 8 randomly chosen people who are willing to volunteer for this study. Half the volunteers take the old tablet, half take the new. And after a while, we measure the medication level in their bloodstream. Then we wait several days. The reason for that is to flush the medication out of the people's bloodstreams. And then we flip. The people who took the old tablet now take the new, and those who took the new now take the old for several days. And again, they do a blood test. And at 0.05 significance, we want to check if there's evidence that the medication level is higher with the new tablet. So now let's pull up the data in the file section 6.5 tablet. It looks like this. So here are our 8 people, and here is their, in the first column are their blood levels with the new tablet, and in column B, the blood levels with the old tablet. So we want to decide how to do a hypothesis test here. Let's go back to the notes a bit. And first thing we have to do is say, okay, are these independent or dependent samples? Well, again, it's a before and after scenario. So we'll pair each person's blood level with before or taking the old medication, old tablet, with that person's blood level taking the new tablet. These are definitely dependent samples. So we'll have 2 population means. Mu sub old, the mean level with the old tablet, mu sub new, the mean level with the new tablet. And we're trying to check if the medication level is higher with the new tablet. So the alternate hypothesis can be mu old less than mu new, or same thing, mu new greater than mu old. And that leaves this for the alternate, for the null hypothesis. So we have dependent samples. I'll go here to Excel. This particular test, fortunately, is built into the data analysis package. So if you go to the Data tab and choose Data Analysis, there is, near the bottom, several types of hypothesis tests that we can do. The one that we want is right here, t-test, paired to sample for means. So we want to do a t-test, and the fact that it's called paired refers to the fact that we have a pairing, we have dependent samples. So that's the one I want to choose for this problem. Do that, and here's the dialog box. It's saying, okay, tell me where the first variable is stored, so I can drag down through this column. Tell me where the second variable is stored. I can drag down through this column. I can ignore this box. I'll check labels because I highlighted them. I'll leave the level of significance at 0.05. And then you can either have Excel put the results in a new tab, or I'm going to click this button and then click this box and finally click on a blank space in my worksheet. So now it's ready to do the test, and I have it do it and get a response like this. And I'll enlarge the first column a little bit so we can see it. And what you want out of this are two things. One is right here, the test statistic, or T statistic, and the other is the p-value. And you have to be careful which one you pick here. The test is one-tailed, right? We wrote an alternate hypothesis with a less than symbol. That's a one-tailed test. So I'm thinking about mu new actually being greater than mu old, so I could think of this as a right-tailed test, for example. But anyway, it's one-tailed. So when I go to my Excel printout, I should pick up the p-value for a one-tailed test here. It's 8.86, and this is scientific notation times 10 to the negative 5. Go back on my worksheet as I'm, say, reporting my homework. I could say from Excel, we get t equals 7.2 and p equals 8.86 times 10 to the negative 5. I proceed and finish the hypothesis test the way I always do. Compare the p-value with the level of significance, 0.05, and it's much, much less. This is a very small number, much less than 0.05. So that probability is too small to be believed, and I'll reject the null hypothesis. And we can finish by saying at 0.05 significance, there is significant evidence. Then I state the alternate hypothesis in words, that the mean medication level is higher with the new tablet. T equals 7.2, P equals 8.86 times 10 to the negative 5. All right, and last example. Another education activity, trying to decide whether a certain activity is useful in raising third graders' reading level. So we have directed reading activities, and a group of 21 students took part in those activities, while another group of 23 students did not. So as you probably know, in scientific studies, typically you have a treatment group that's taking part in whatever experiment you're running, and a control group does not. Then we have both groups take the same reading test, and the data is in section 6.5 reading, and we're supposed to check the claim that the mean score who participate in the activities is higher than the mean score of those who don't. First thing, we have to decide whether the samples are independent or dependent. In this case, even the sample sizes themselves can tell us there are 21 students who did take part in the activities and 23 who did not. There are different, the sample sizes are different, so I really can't pair them. And even more fundamentally, there's really no connection between those who did take part in the activities and those who didn't. They're different students. So these are independent samples. So let's let mu sub ACT, or activity, be the mean reading score of all those who would do this activity, and mu control be the mean reading score of all those who didn't or wouldn't ever take part in this activity. And I'm trying to check if the mean score is higher among those who participate in the activity. So I could write it this way. And looking for a tail, this is a one-tailed test again on a t-test. Now the samples are independent. So I go to my section 6.5 reading folder. We'll run a hypothesis test from data analysis. Now we choose a different one, and it is this one, to sample assuming unequal variances. So there are several types of two sample tests here. The only two that we'll use are the one we just did, paired two sample for means. That's when we have dependent samples. And the other we'll use is two sample assuming unequal variances when you have independent samples. That's what we have. So I'll choose this, and it similarly asks me for where is the first sample and where is the second. Again, I'll check the labels box, and I will have Excel put the results here at some blank spot in this worksheet. So it looks like this, very similar. And the two numbers that I'm interested again are the t-statistic and the p-value. This was another one-tailed test, and so here is the p-value. So from Excel, I got these two numbers. The p-value again is much smaller than the level of significance, so I reject the null hypothesis and say at 0.05 significance, there is significant evidence that the mean reading score is higher among those students who participate in the activity. T equals 2.31, P equals 0.013. And that's really all we'll need to do with this particular topic. We'll stop there. Thanks.